Hi, my name is Enebeli Chidubem. I'll be running through my research work, which is dynamic model or architecture for service composition. Thank you. Dynamic model for web service composition is the use of reinforcement learning algorithm in web service composition. Different works have been done on this in the past. However, in my research, we'll be comparing web service composition reinforcement learning frameworks that take into account difficulties of dynamic service settings and also seeks to maximize QoS use and the user satisfaction. Also, in my design, I will be stating out the different paths, should I say, edit states, the actions, having web service composition, and multi-objective service composition. This is one of the recent studies on the use of reinforcement learning for web service composition. However, this is multi-objective service composition, though. Then we'll move down to our experiment design. The algorithm to test here, like I said in the introduction, I'll be picking out two different algorithms. We have the Q-learning and the autocritic. Now, in order to start up our design, we'll have the states to be defined. We have a set of states which ranges from the initial state to the last state in the environment, and also the set of actions which ranges from the initial action to the last action. Action in this web service composition aspect can also be referred to as service. Then we have the reward matrix to define. Um, in the reward matrix definition here, we have to evaluate the QoS. QoS is the quality of service. The quality of service here has to do with the parameters that define the quality or how good a service is. For instance, the availability, the response time, and so many of them. So those have their values, and we have to reevaluate them in a way that we can bring such the set of services and their values into the simulation. It could be the Q learning or the autocritic. Now, as for the QoS evaluation, to define our QoS in our system, we can say that it has to be the service name and the set of services or the QoS, rather the service name and the QoS of that service. In a situation whereby we have the services have more than one QoS, it can be evaluated in order for each service to have or maintain a single value for the set of excuse me, for the set of QoS parameters it has. Now, this mathematical representation here represents uh, the evaluation of the QoS values or the QoS parameters. Then I'll be explaining the values here. The WI, just as we can see here, is the weighting factor. And then to get this weighting factor is having the total number of columns, which is the total number of parameters, QoS parameters, divided to divide one, which is one over the total number of QoS parameters, which means that each value when summing up the total value of this uh, evaluation here will give us a total of one or less than one. Then in our Q-learning algorithm, we have the temporal difference and the Q-learning Q-values update. As a part of this which is highlighted here, this part of this formula is meant for the temporal difference or in other words, I can say is the temporal update or TD update or the learned value, which combines the reward value and a discounted value from the offset of new states and action minus the the current states and action. So there's also a value within this formula which is called the learning rate or rate of learning, which defines how much um, learning that can the Q value can obtain. And we have the arrow as the reward, while this as the discount factor, as I have explained before. Then the max A is like the optimal value um, in a set of actions. It can randomly pick an optimal value there. So that is what this represents. Then the QSA is the current key value, and the QS with the exclamation there, the hyphen there, rather, is the next state and the next action of the key value. And like I said before, this highlighted here, and I highlighted it before, is it can be seen as a temporal difference or the TD update, temporal difference update. Now, in the critic algorithm, which, as I explained before, is a combination of the policy-based and the value-based, and of course, it's been widely used in reinforcement learning. In this aspect, the policy-based component operates as the actor and is accountable for being familiar with the decision-making policy for action selection. Then, in the critic, which behaves more like the Q learning part, is a value-based component, and it learns how to estimate the value function to judge the value of states during the learning process. Now, the formula or the mathematical representation for autocritic algorithm is this. In this, you also need to find the TD, but in this aspect is the TD difference or the temporal difference or the TD error. Okay. Now, it looks more like the one in the Q-learning algorithm. However, the difference here is we also still focus on the value, the Q values, which is the critic Q, which is more like a Q tables in Q-learning is also the critic here. So the critic is for the values and the actor is for the policy. All right. So the discount factor also used there. Now, in this aspect, you define for critic the key tables for the critic and the key tables for the actors, and they are almost the same, just that the difference here is the actor key table makes use of the actor learning rate, and the critic key table makes use of the critic learning rate. Now, for our performance evaluation, like I said before, I'll be using the cumulative rewards. Cumulative reward is the summation of all the rewards in the total steps, the total rewards in each step per episode. So you sum up all the rewards gotten in every episode to give the cumulative reward. Okay. Now, also my research analysis, I discovered that yes, the Q-learning converges and the autocritic converges, but not in the same way. Now, I also discovered that the higher the number of episodes, the more visible the convergence we can find in autocritic algorithm. However, the Q-learning converges so fast, though. Also, in my findings, I discovered that there is this staging between stable and unstable convergence in Q-learning. In this aspect, while doing this experiment, I discovered that in my Q-learning, that if I reduce the value of the epsilon, um, the epsilon value, that my convergence would start tilting from being converging to becoming a diagonal straight line. Okay, then if I start increasing the value, it would increase, and it will give us a smooth convergence, a smooth learning curve. In every of the data set I've used, it appeared to be the same way. So I have a sample experiment here. I did for 4,000 episodes, and in those two, I maintained the same value for discount factor and the learning rate. However, the epsilon value was changed. So I first used zero point 0.2, and it gave me the graph on the left hand side. And in another test, I did maintaining the same discount factor and the learning rate. I did the epsilon value to be zero point 0.8, and it gave me this smooth curve here. Then, like I said, in my discovery, I just noticed that while moving up, like from zero point 0.2, changing the epsilon value, when you get to zero point 0.6, it will converge. But when you repeat that same test on the same epsilon value, sometimes the convergence wouldn't be stable. It wouldn't converge. It would just tilt and change shape, and then it wouldn't have the same value that you can get when you move higher. Then on zero point 0.7, I also noticed that it was doing the same thing, however, but it wasn't regular. It in five tests of the same epsilon value, it can converge very well for four, but one of them wouldn't converge. For the zero point 0.8, no matter the number of tests that I ran for that epsilon value, it kept converging. So this is where I noticed that in a situation where the epsilon is not high in my point to a particular epsilon value, where the convergence will be very much stable. All right, so at the end of the test, at the end of the test, we have a table for the performance comparison. However, there were other ones, other tables, and then other graphs. For instance, the CPU usage, the memory utilized, and the policy loss too. So, but in this presentation, I would just focus on the cumulative reward table and chart, because this is the major part that says, oh, this algorithm behaves or does better than the other algorithm. So in my test, in my experiment, I noticed I used a data set which has 2507 rows, and I had different episodes that I did the test with. Then in the cumulative rewards, I discovered that Actor was doing better in terms of the value returned than the Q-learning algorithm. And in their different episodes, I have the values here. Okay, so I also had to project this in a chart. It gave me this type of chart. So in my interpretation, I noticed that Autocritic does better in terms of reward accumulation. However, in Q learning, the speed of execution was a bit better, but the focus for the web service composition. So the next thing is to demo the program. Here I have the Q learning file, the Python file, and also have the Autocritic file. So I've set some parameters, the values, and I also set for the same thing for the autocritic as well. So I'll start the application and then we would see, I'll start the two of them and we'll see their convergence. All right, thank you. Okay, so the Q learning has completed is the program has completed, and you can see the convergence. You can see the graph or the cumulative reward graph for Q learning. All right, thank you. Also, the autocritic also the program has been completed. They are completed almost the same time, and this is the autocritic learning curve. You can see the convergence. You can see the total reward gain here too as well, or should I say the reward gain pattern. Okay, thank you.